Hello, everyone. My name is François Rheault. I'm a postdoc at Vanderbilt University under the supervision of Dr. Bennett Landman. Today, I'm going to talk to you about tractography file format, reference space, and how to correctly use them. This is a very dense and charged subject. I could talk about it for 2 hours, but this is going to be an introduction to various concepts just to make sure people understand the implication of such things. So to talk about tractography, I really need to talk about the Nifti file first. So it's a way in to the tractography in the rest of the talk. So first important thing to know about the Nifti file format is that it's a neuroimaging multidimensional array file format. And the easiest way to understand how it's organized and how it works is to start simple with the multidimensional array. So talking about the grid or sometimes data, volume, or array, what is the number of voxels present in the Nifti file? What is the dimensions? What are the dimensions? What is the shape? So this is an example of a very simple three-dimensional array. The first one is 4 by 5 by 4 because one axis is bigger than the other. If it's a cube that is 4 by 4 by 4, the total number of elements is 64. So very simple concept. And I'm going to use this 4 by 4 by 4 array for the rest of the Nifti presentation. Very simple question. How do we fill a 3D array reading a 1D vector? So if we have a Nifti file that has a sequence of value to represent the data, it's a 1D vector that is sequential. How do we fill this 3D array correctly? So there is more than one way of doing that. And this is the complexity of the Nifti already starting. If we want to fill the 3D array, there is 8 possible starting positions. So this is the same array with a better view. You can either start the 1D array, so the red cube right here. You can either put it in this corner, that corner, this corner, that corner. There is 8 possible starting positions. So from 1D vector to 3D array, there is already 8 choices. But then what do you do after that? Where do you put the second one? Where do you put the orange cube? Well, the orange cube will go either in this axis, that axis, or this axis. So there is 3 more choices, the direction of encoding, so X, Y, Z. So we already have 24 different ways of filling a 3D array with a 1D vector. And you can see it here is an example with this corner as the first one. And this is another example with that corner as a starting point. So we have 24 ways of doing that. But once that line is filled, where do you go from there? Well, you have 2 more choices. Either you fill that plane first or you fill that plane first. So now you have 2 more choices. So you see 8 possible starting position, 3 possible direction of encoding, and 2 more choice for the plane order to fill. So you can see already we have 48 ways of filling a 3D array from a 1D vector. This shows the complexity of the concept behind the data structure of a Nifti file. And you don't have to exactly remember like how it's represented, but it's important to know that this information of how to fill the 3D array is known as the stride, or sometimes referred to as the voxel order. So if you are in one scenario, starting from one corner, filling the x-axis first, and then filling the y-plane second, it's going to be a stride that could be 1, 2, 3. If you switch corner or you switch plane, you're going to have a different combination of those values right here. And these 3 numbers will represent those 48 possibilities. Sometimes it's referred to as voxel order. So for example, 1, 2, 3 is RAS, where 1 and -1 mean right and left, 2 and -2 are anterior and posterior, and 3 and -3 are superior and inferior. So this voxel order or stride is how you go from a 1D array to a 3D array. So the dimension and the stride are 2 attributes of the Nifti file that refer to what we call the voxel space. It's only about the grid. It's really just about the cube of data. There is nothing else. So dimension and stride. But the Nifti file is not just a grid. It's not just an array. There is also the concept of spatial transformation. We also refer that to like the Nifti affine, the Nifti header. This is a very important component of the Nifti. So let's take a look at that. So first, the voxel space, dimension and stride, and now the spatial transformation. For those of you that are not familiar with linear algebra, let's just see a small simplification of what is the affine transformation. So if you have your cube, so the 4 by 4 by 4 from earlier, and you want to transform it and give that cube a certain size, a certain shape, you can transform it using a scaling factor. So if you have an affine matrix right here, it's a 4 by 4 matrix. The null transformation is the identity matrix, so 1, 1, 1 on diagonal. That would be considered no transformation. If you put a scaling factor in the x, y, z, so first column, second column, third column, you're going to scale that cube in different axes. So for example, this 0.5, 0.5, 0.5 will make your cube smaller. This will provide a correspondence between your grid and the size of the grid. So now you're scaling it to its actual size in the real world. So that's a scaling matrix. You can also have a translation. So if you want to say that the person was moving in the scanner, you have to translate your grid somewhere else. So you need to apply a transformation that represents the X, Y, Z translation. And this will allow you to put an actual position to your cube in space in relation to your scanner. There is also a rotation matrix. So you have a X, Y, Z rotation matrix that corresponds to rotation of your cube. And you can summarize that into the 3 by 3 matrix that you can see right here. It's going to give a small rotation in multiple axes. And this will represent how the person was oriented in your scanner. And you can fuse all of these into one matrix where you have your scaling factor, you have your rotation in this 3 by 3. It's all multiplied at once, and then you get that thing, and then you have the translation in the last column. And this affine transformation will present what I showed before all at once, and it's going to take your cube, move it somewhere, rotate it, and scale it. So that's the affine transformation. And now we are in what we call world space, scanner space, or RAS-MM. This spatial transformation will provide a real size to your grid, will provide a real size to your voxel, and will give you a real position relative to the scanner. Like I said, if the grid is sometimes called voxel space, well, this new concept of a grid position in space is called world space, scanner space, or RAS-MM. Now, if we go into tractography file format, why did I talk about that? First is because if you want to save streamline, you need a convention. If you want to understand where your streamlines are in relation to something else, you need to understand how Nifti does it. And you would expect that if you write streamline in a file, they should overlay with your Nifti, they should overlay with a reference in different software. So it's important to understand both at the same time. Today, I'm going to talk about two main conventions, the TCK and the TRK. Both are supported in Dipy. TCK is typically from MRTrix, and TRK is typically from TrackViz, and there is also DSI Studio that uses it, for example. The TCK file convention for the streamline is to write the streamline as XYZ in world space. So the transform cube I mentioned earlier with a real size and a real position, that's the world space. So TCK writes their streamline directly into that space. And there is some pros and cons to that. It's easier to understand and to manipulate, but it requires a Nifti for some operation. Then there is a TRK file that writes on this, the streamline in voxel space, following the same convention as the Nifti. This does not require a Nifti file because the TRK is self-contained. There is a header that contains the transformation, just like the Nifti. So the TRK is a lot more analogous to the Nifti than the TCK file. But the downside of that is it's harder to understand and to manipulate for a lot of people. I'm gonna just give a small mention to the TRK file. It's important to know that when you're writing lines to a file, there is different convention, and you can interpret what you wrote different way. So if you write streamline as a 1D vector, just like the Nifti we mentioned earlier, so it's a 1D vector, and then you want to interpret that as streamline, you're going to need to interpret the coordinates. So for example, here you see triplets of values. This can be seen as the 3D coordinate. But how do you interpret that? Is it XYZ, 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 XYZ? Or is it something like ZXY, ZXY, ZXY? And it's important to know that there is a convention. And for example, for the TRK file, you need to be aware of that convention. Because if you switch that, or if you get confused, you forget about the convention, you can load the streamline as XYZ, XYZ, and you're going to see your streamline going in one axis. But if you actually wrote them as zxy, zxy, the streamline should have a different orientation. Same thing if it was supposed to be yxz, yxz, yxz. So by changing your convention, by changing the equivalent of the stride for the streamline, you have the same thing as the cube I mentioned earlier. So how to write a cube from a 1D vector, you can have how to write a streamline from a 1D vector. And it's just important to remember that this is a thing. This is not necessarily important for most people, but just so you know, different software will read wrong a file or write a file wrong, and then you end up with challenge when you switch from Dipy to MRTrix to MITK to DSI Studio. And it's important to remember that these conventions always get confused between different software and tool. But most importantly, if you're trying to write a TCK file and then you load it, you have to remember that the TCK file write the streamline as XYZ in wall space. And if you want to switch from wall space to voxel space, well, it's very easy conceptually. You have the affine transformation in your Nifti that I mentioned earlier. So this transformation, so it's the same as in the previous slide, is often called voxel to RASMM. So this transformation gives you information about how to go from your grid space, the voxel space, to your scanner space or wall space. So if you load a TCK file that is currently in wall space, so you can see that you have your oriented grid with a specific position and scale, and you have your tractogram that fits, it's in it. They are co-registered, they are aligned. And you want to go to grid space. Well, what you're going to do is inverse your voxel to RASMM and transform it into RASMM to voxel. And you're going to go from your wall space to your voxel space. So this transformation is technically very simple, but understanding the concept is a bit more complex. And if you do the same with TRK, so when you load the TRK file on disk is in voxel space, and you're going to use its own header or another Nifti, they end up being, they're supposed to be the same. You're going to use directly your voxel to RASMM transformation matrix, and you're going to apply this transformation matrix to the cube and the streamline, and you're going to end up in wall space. And you can see that they were aligned before, and now they are aligned after in wall space. This transition from the grid to the wall space, you can see that they are opposite of each other. And the idea is that if you do it correctly, this wall space and this wall space should be the same if they are valid file from the same subject. Same thing if you go this voxel space from the TRK and this voxel space from the TRK should be the same if you're working for the same subject. And the idea is that that's how you can transfer from TCK to TRK. If there is a script that do conversion, you can switch from TRK to TCK quite easily by providing a Nifti file because they follow convention. But why do we need those two different spaces? Well, there is different reasons. So why do we need to switch from wall space to voxel space and vice versa? Well, if you want to, for example, sample FA metric from a tractogram. So you have a tractogram here and you want to know what is the FA at the edge there. What's the FA at the last point of this streamline, or what's the FA in this point? You're going to have to map this to a grid and map that to a NumPy array and do interpolation or just do NumPy accessing. So if you do that, you need to go to world space and say, this red dot corresponds to this red voxel, and the value is 0.3. And this blue dot corresponds to this blue voxel, and this is 0.5. So this transition from world space, from streamline to grid is very important. If you want to count the number of voxels to estimate a volume, or if you want to do TDI, you have to be in voxel space and count streamline. And you have to be able to do that transformation. Why do you need wall space? Well, wall space is very important if you want to do something that requires the spacing or the length or the size of things to be in millimeter. So if you want to compute a convex hull, to compute a precise volume or estimate the streamline length, and after that, just say the length of the streamline is an average 200 millimeter, you have to be in a space where the scaling is right. So wall space is useful for that. But also for registration across data set or intermodality, you need a space that is in common for everyone. And that's a bit more complex, but you can see here in the GIF that if I have 5 modalities, some are isotropic, anisotropic, some have high axial resolution, high coronal resolution, some are cropped, some are not. And you want to say, where is this voxel mapping in all of the other? this is where world space is very useful because they all have a position in space. That's where you can co-register them. It's very useful because now they can be mapped one to the other, but they don't have the same voxel space. A small mention about these concepts is if you're doing some processing in Dipy, such as density map, there's some function that access the NumPy array, and it could crash if you provide negative coordinate or coordinate greater than the grid. Just like in C++, if you want to access an array at position 200, but the array has a size of 100, it's going to crash because of the memory allocation. So this is one of the reasons why grid space, it's important to understand that this is just an array. There is no size or there is no coordinate in 3D. It's really just a grid. So if you have streamlines or a tractogram with streamline outside of this voxel space, it shouldn't be considered valid because your tractogram should be constrained to the volume from which it was generated. So we call these invalid streamline, and this is an example. If you have a streamline that's mostly inside of the volume, but at some point it gets out, this streamline could crash some algorithm that require accessing an array in memory. And that's why we have to remove them. And we have function 12 for that. I'm going to talk about it a bit later. So this is a concept of grid space, voxel space, streamline that are invalid because they should not get out of an array from 0, 0, 0 to grid's dimension. There is a lot more to understand to that. There is also the concept of shift. Like if I say voxel 0, 0, 0, do I mean this corner or do I mean the center of the voxel? That's also a convention. There is also intermediary space called Vox MM. You can also try to map VTK surface to tractography. This is also a question of reference space and convention. How do you do linear and non-linear registration of Nifti versus tractogram? If you have question about that, I would be happy to help. If you have question for the Q&A after, I would be happy to help. But there is a lot more to it than that. I could talk about those conventions for hours. I'm not sure everyone here would like it. But in order to help people, that's why I did a pull request in Dipy last year or 2 years ago with the stateful tractogram that was supposed to help people with manipulating those reference space in the file format. So this can load TRK, TCK, VTK, Dipy file format. It always requires a Nifti file to ensure consistency. And to ensure consistency, it also have a strict loading and saving routine to avoid mistake. There is also helper function to switch from voxel space to world space. There is function to remove invalid streamline and also to help verify the compatibility between spaces with headers of TRKs and Nifti. So I will show a bit of that code in the IPython notebook I have ready. I hope this will help people, but this class is basically a wrapper class that will help people manipulate Nibabble tractogram or like transfer from TCK to TRK more easily. I also wanted to have a quick mention of a community file format that we are working on called the TRX, because 2 years ago, it started very small. Someone asking question about having a unified file format because it's hard to switch from software to software. A lot of people complain about current file format that are very large, no compression, it's not very efficient. Partial loading is difficult sometimes. Spatial transformation are non-trivial. So that's why we came up with a list of what we wanted to do in the new file format. So spatial transformation that are easier to process, more feature that could be added in the future, conceptually simpler, a lot of memory saving or hard drive saving using compression. And this was discussed between people from MRTrix, Dipy, DSI Studio, different software library like Dipy, and all of that was a community effort to come up with a list of requests or like what we desire for a file format. And that's why I did a proposal for the TRX that was kind of a compromise between all of these groups, trying to achieve as many bullet points on our list. And recently in December, we did a small OHBM abstract to present the proposal. And everyone on the paper was from the GitHub where we all discussed. Everybody gave me feedback and suggestion for the abstract, and it got accepted for normal presentation at OHBM. So if you want to talk about that here or at OHBM, I would be happy to help. This is a small mention of, file format evolve, and sometimes they will get easier to use or like more complex. So it's just important to know all of these conventions. And now I'm going to switch to the IPython notebook that I have here. I'm going to start at the top and restart my kernel and clean everything so I don't get confused. So this is just a small example that you have available on Google Drive. I'm going to give the link where if you want to manipulate those different spaces, you just have to know about certain tricks with the function. So right now, I'm just going to import what I need. Here, I'm going to fetch a bundle from Dipy. So I fetch 5 bundles with different file formats. And here, I'm going to try to load them using the stateful tractogram. So here, I'm going to set the logger to debug so I see everything. And I'm going to use this function with my bundle file name and a reference anatomy. So that's a Nifti. The Nifti is required for everyone, just like I mentioned earlier. So I'm going to try to load that. I'm going to see some information from the debugger where I show the affine transformation. You see it's almost the identity, almost 1, and there is big translation. Voxel dimension, voxel size, and voxel order stripe, RAS. And then there is a crash here because the last two, so the LPT and RPT, are equivalent to the CST. So they go down the brainstem and they have invalid streamlines. So right now it's warning me with bounding box is not valid in voxel space, cannot load a valid file if some coordinates are invalid. Please set BB box valid to bbox valid check to false and use this function to remove the invalid streamline. So I'm going to just load them, putting the check to false here, and it's going to load easily. I'm going to come back to it later. So here I will just print the spatial transformation information I listed earlier. So this is great. And my first task here will be to compute a density map using a Dipy function. So there is 2 ways of doing that that's going to end up being almost identical. It's a tiny difference, probably due to float 32 and float 64. Don't worry. First thing, I'm going to resample my streamline to 100 points, and I'm going to have my streamline in wall space and call the density map function with an affine and the dimension. This will allow me to compute a density map that will be correct in terms of dimension. So they will have the right size in terms of number of voxel. And the affine will allow me to switch from my wall space to my voxel space for the computation. So I'm going to just compute that. Then the second approach is to have my streamline already in voxel space and not provide the transformation. So you can see that these two are kind of equivalent. If I put them in wall space, I need the affine to go back to voxel space. And if I'm already in voxel space, I don't need to give the affine. And this will give me 2 density maps that are by any mean like identical. There is like a 0.1% difference, or maybe even less than that, but they are the same density map. So you can see that these 2 approaches are the same. Now, if I come back to my example earlier with the invalid streamline, if I run the exact same code for that streamline, but I do not remove the invalid streamline, I'm going to get an error. Because there is invalid streamline in my tractogram, and then when I get to this function, I get an error that tells me streamline as point that map to negative voxel indices. And NumPy doesn't like that. In fact, it's probably in Cyton, or it's basically checking if there is something wrong with it, and there is something wrong with it, so it crashed. So what I'm going to do here is remove invalid streamline and immediately rerun this. And the first approach or the second approach will work, and you end up with pretty much the exact same density. So that's a great thing. The invalid streamline were problematic, and we can remove them easily. So this is an example of that right here. Then I have some visualization function. I'm just going to compile that very fast. Here, I'm going to just show what I computed. So you can see here, I have my corpus callosum with the density map behind it. So they are aligned. I'm happy. It's perfect. If I show my corticospinal tract, there is a density map behind it. It's great. You can see that everything is aligned. It's perfect. Then what I'm doing here is I'm summing the density map and the streamline. So I'm going to show them at the same time. So you can see again, they are aligned. It's great. Okay, so that was the first part of it. If there is any question, ask me in the QA. You're gonna have some access to that later on the Google Drive for the conference. Now I'm gonna show you different MNI 152 with different resolutions. So what I'm gonna do is show the voxel space of different MNI map. So I'm gonna just show the grid. So they're gonna have different size. So this one is in 1 by 1 by 1. This one is in 2 by 2 by 2. This one is anisotropic, so 1 by 1 by 3, 3 by 1 by 1, and 1 by 3 by 1. And I'm gonna just show the grid itself. So the first one is very easy to understand. It's just an MNI map. It's fine. The second one is in low resolution. So you can see it's the same map. It's just low resolution, and the voxel are much bigger. Then this is anisotropic one. So the voxel in this axis are very large. So the grid looks squish in that axis in voxel space. And if you want to comment these lines by yourself, you're going to see what's the difference between the world space and the voxel space of those maps by yourself. And these are in the other axis. So I was just showing all of them. And now we get to the real challenge of looking at streamline on top of Nifti file. How do we make them align? Sometimes in Dipy, people load things and like they don't necessarily match. And why are they not matching? So what I'm going to do here is load a TRK file using its own header as spatial transformation reference. And I'm going to load the TCK file with my MNI Nifti file. I'm going to just check that they have compatible header. It's going to print through and through because that's fine. And what I'm going to do here is give my grid and my streamline and look at it. So this looked wrong. Why does it look wrong? That's because I gave my grid and my streamline, and by default, my streamline are loaded in wall space, and my grid is just a grid. So this is in voxel space. So they are not aligned. So what I'm going to do here is provide the affine transformation to my grid so I can do that mapping. So the next one is going to load on top of each other because they're going to show the grid and the streamline in wall space. The second approach to that is bringing the streamline to vox space. So you can see here, I'm switching the streamline to voxel space with the function toVox. And now I'm going to show my grid with the streamline, and they're going to look aligned because I decided to show voxel space. So that's an example of how you can visualize your thing correctly. Now I'm going to do a bad example where I'm going to load a TCK file with a reference in 2 by 2 by 2. But I'm going to do my visualization with my MNI in 1 by 1 by 1. So it's pretty much the same logic here, except I used the wrong header. And you can see here, affine is not equal, and that test is false because my TCK and my MNI space don't have the same header. So these are showing as incompatible. So just like before, they don't match because right now this is voxel space and this is wall space. So they don't match. This is in wall space. So now it looks like they're matching because they are in the same position in space because of my wall space being the same. It's MNI 152. But the next one, I'm going to try to look at my voxel space. And now it won't match because they don't have the same voxel space. This one has a voxel space with a spacing of 2 millimeters. And this one is my grid in 1 by 1 by 1. And this is why this one looks 8 times smaller. It's because they don't have a matching spacing, matching voxel size. And when you go to voxel space, nothing makes sense between those two. So the solution to that is either visualize, correct the header. So that would be the first solution. Use the correct header at the very beginning here. So use the same reference instead of using a MNI versus MNI 2 by 2 by 2. Or the second solution would be to go to voxel space, but using the right transformation. So using visualization on the 2 by 2 by 2 data. So now if I quit, you're going to see they are aligned in voxel space. And this one is in low resolution. So now they have the same voxel space because I'm looking at the TCK that I loaded using the 2 by 2 by 2, and I'm looking at the grid of the 2 by 2 by 2. So they have the same voxel space. And now this is pretty much the same example with the 1 by 1 by 3. It's just more extreme and easier to look at. So if I run this one, just like all the other, these don't fit because I loaded this tractogram in wall space and this grid is in voxel space. So just like the 3 other cells, these don't match. Now I'm looking at the wall space. So they do match again because it's in its center in MNI 152. They have the same rotation. So in wall space, they do match. But next, I'm going to try to look at the voxel space. So I'm going to use, again, a 1 by 1 by 1 voxel space with the streamline with the 1 by 1 by 3 reference in voxel space. And these won't match. So you can see here, you don't see a streamline, and the streamline are squished there because this 1 by 1 by 1 voxel space is, just like that, and this voxel space is squished in one axis because it was using the wrong reference. So a solution to that is to first always use the right reference, even when you do visualization, even in wall space. So this is matching reference in wall space, and this is matching reference in voxel space. So it's always important that when you do visualization, you look at your streamline on top of a Nifti that does match with it. So if you have any question, I would be happy to answer in the Q&A after. And a small last mention about the tractography and different way of doing tractography. This is copy pasted from the tractography, the tracking local PFT tutorial. This is just the initialization from the tutorial. So I'm going to fetch some data and load my diffusion, load my label, and load my tissue map. Here, I'm making sure that my tissue map and my diffusion and my label and my diffusion all have the same header. So this is going to print through twice right here. So this is a good sign. So my label, my diffusion, and my white matter mask have the same thing. What I'm doing here is I'm going to declare my tractography. I'm going to start my tractography process. And there is 2 ways of doing that. You can declare all of your things in wall space. So you can see here, you're creating seeds and you're creating a criterion based on voxel size, and you calling your tracking function using the affine. So all of this is going to be in wall space. That's why we're providing the affine. We're checking the voxel size in millimeter. The step size is 1/4 the voxel size. That's in millimeter, and there is the affine right here. So all of this operation will be in wall space. I'm going to launch it right now, so it's computing. And when it's going to be done, I'm going to save a TRK file using the stateful tractogram. And I declare the stateful tractogram here, saying my streamlines, this is my diffusion, this is my reference. And right now, the streamline are in wall space. So I declare my stateful tractogram in wall space, and then I save it because I just generated it in wall space. So it's very important not to get this wrong. Because if you get this wrong, it's going to interpret the streamline wrong and then save something bad. And then I do visualization, and you can see here, I'm adding my grid. That's a white matter mask with the affine. So I'm telling him, show me wall space and show me streamline. And they look on top of each other. So this is great. The streamline are aligned. They are in wall space. But there is another way of doing that. It's almost identical. But here you see that I'm declaring the seed. I say, don't take an affine. This is the identity. Voxel size is not in millimeter. So I just say 1, just like 1 voxel. My step size is 0.25. So it's like 1/4 of a voxel. I don't give the affine here. So basically now I'm going to do my tracking in voxel space. I'm going to start that right now. And I'm going to declare my stateful tractogram slightly differently. So the streamline that you're going to give me are going to be here. That's my diffusion, just like before. But right now, my streamline are in voxel space. So I'm declaring my stateful tractogram slightly differently. And it's going to create my stateful tractogram, and I'm going to save those 2. And they're going to be both valid. And here I'm doing visualization, just like before, where I say, here's my data. I don't give the affine because I will be in voxel space, and I give my streamline that are in voxel space. And now they still show on top of each other. So that's a good thing. And you can see that those 2 cells are basically equivalent, except three different things. This is in millimeter. You have an affine. This is in voxel, and this is identity transformation because we're in voxel space. And then we do the saving slightly differently, and we do the visualization slightly differently because we are not doing those two cells in the same space. And it's important to understand this slide variation. So this is pretty dense, pretty complex. You have this available to play with to see the problem. I would be happy to answer a question if there is any at the Q&A after. So I hope you enjoy the presentation and that you learned something. I would be happy to answer email or set up discussion during the DIPA workshop. So I hope you enjoy and have a nice day.